Section 5, Video 5, Resource Management with Memory. In this video, we'll learn how resource management manages memory of a virtual environment. We consider host memory is overcommitted when the total amount of guest physical memory of running virtual machines is larger than the amount of actual host memory. This has two distinct advantages. Higher memory utilization. With memory overcommitment, ESXi ensures that host memory is consumed by active guest memory as much as possible. Another added benefit is a higher consolidation ratio. With memory overcommitment, each virtual machine has a smaller footprint in host memory, making it possible to fit more virtual machines while still achieving good performance for all virtual machines. As shown in the picture below, using memory overcommitment, we are able to run 3 virtual machines with 2 gig memory configured on this host with 4 gigs memory. In the event that memory overcommitment was not possible, we could only run a single virtual machine, as we have to take into account the overhead memory as well. So with memory overcommitment, we do get a higher consolidation ratio. The other topic we look at is memory reclination, which is a process of borrowing memory from virtual machines that are idle or not using their memory and providing it to virtual machines that are requesting or actively asking for memory. ESXi uses following techniques to reclaim memory: IMT, or idle memory tax. The hypervisor ensures a VM is actively using its memory, otherwise an idle tax is imposed. Virtual machines, VMware tools inside the virtual machine uses a balloon driver to determine the memory blocks that are allocated but idle. This, however, is not a dynamic solution. Let's look at dynamic memory reclamation techniques. We look at 4, which are transparent page sharing, ballooning, memory compression, swap to disk. The interesting thing to note here is the order. The ESXi host will go through this in order as listed here when it's faced with memory contention. The first technique it'll try is TPS. If that doesn't work, then ballooning, memory compression, and then finally swap to disk, which incurs a huge performance penalty. In the next slides, let's take a look at these techniques in detail. TPS, or transparent page sharing. ESXi uses a proprietary page sharing technique that securely eliminates redundant copies of memory pages. A workload of identical virtual machines, let's say Windows 2016 servers running. With such a workload which has identical virtual machines, there is higher opportunity to remove or reduce the redundant copies from memory, and as it shows here, you can free up to 30% of memory. With a more diverse workload, let's say including Linux and virtual machines running Windows, the saving might be 5% of memory. Do note that TPS is not enabled by default. Ballooning is the next technique that ESXi host will try when faced with memory contention. This is a very innovative technique, and balloon driver gets installed with VMware tools, so it's always best practice to install VMware tools on every VM that's configured. When the ESXi host is running low on physical memory, it will contact the balloon driver to talk to the guest operating system and try to borrow some memory. The innovation and genius of ballooning is that it allows the guest operating system to make the hard decision, which is to say which pages can be paged out without the hypervisor's involvement. This allows the ESXi host to safely borrow memory from the guest operating system and provide it to another virtual machine that is actively requesting memory at that time. Once the memory contention phase is over, the memory can be returned back to the virtual machine that it was borrowed from. In the reclamation techniques, the next one is memory compression. When memory is overcommitted, ESXi can compress virtual pages and store them in memory. This is still a magnitude times faster than swapping out to disk. The pages that can be compressed to 2 kilobytes or smaller, meaning there's a 50% chance or likelihood, those are moved to a memory cache on the ESXi host. The size of the compression cache can be set. By default it's 10%, indicating for a virtual machine with 1000 megabytes configured memory, the cache that's set up on the ESXi host is 100 megabytes. The last technique, which is swap to disk, actually incurs a huge performance penalty, and let's see what are the reasons. ESXi host uses hypervisor swapping as a last resort to reclaim memory. This is the fourth step, and this is taken when all the three that we looked at earlier have failed to relieve that memory contention. A swap file is created for the virtual machine at startup, and the hypervisor can directly swap out guest physical memory to the swap file. This comes with a higher performance penalty, and there can be additional issues due to page selection problem. ESXi host is unaware of the active memory pages that the guest operating system is using, and during the swap to disk it can just take those pages and swap them out, resulting in performance degradation on the virtual machine. A double paging problem where the virtual machine is also paging out the same memory page while the ESXi host hypervisor is doing the same. And finally, the high swap in latency, when the same memory pages are read back from slow disk I/O system, it results in a higher latency. Page selection and double paging problems exist because the information needed to avoid them is not available to the hypervisor. To summarize, we looked at memory overcommitment and how it benefits a virtual environment by allowing higher consolidation ratios, and we looked at memory reclamation techniques which the ESXi host can use to elevate memory contention. In the next video, video 6, we will be looking at resource management from a CPU perspective. Thank you for watching.